rhombus, circumscribed, angles, this thing. It's geometry. With me, Miss Cohen.
We are doing a new lesson in our notebooks today. So before we get into it, I want to make sure your table of contents is all set up. This is what we've done so far this year, and these are in the wrong order, so you should have them in a different order. But for the last 3 lessons, we've been working in our rigid transformations book. So we're going to go ahead and just write 2.1 to 2.3. That was transformations, and I don't know what page that'll be on, but you will turn to a new page and glue your book onto that page at some point. And then today we're going to be doing lesson 2.4, which is symmetry. So pause if you need to get all that down, and then I'm going to turn to my next blank page, which is here, and I will go ahead and glue my rigid transformations book onto that page at some point, and then turn the page, and these are today's notes. So I put today's date, but you put whatever it is when you're watching the video. And then the essential question, how do you determine if a figure has line symmetry or rotational symmetry? And we're going to start today by doing a demonstration. So we will take notes, but for right now, you can just get this down and then put your pen down and watch the next 5 minutes or so of the video. Hi class, today we're talking about symmetry. And we know probably vaguely what that means. Like if something has symmetry, then it's the same on the left and the right, or you can fold it in half. So you've talked about symmetry before, but today we're going to get a little more technical with our definitions. So I have here an equilateral triangle, and it does have a lot of symmetry. So it has several types of symmetry. We're going to talk first about line symmetry. And line symmetry is when you can reflect a figure over a line of reflection and have it map entirely onto itself. So here's what I mean. Here's my equilateral triangle, and if I move this line of reflection, say here, and I reflect that purple triangle, it will reflect over the line somewhere else. So what I want to do is see where I can put that line so that when it reflects, it maps perfectly onto itself. So the way we could do that is we could try to put the line like on the triangle somewhere, right? So I could maybe put it right there. And I want you to think about, if I flip the triangle over that line, will it map onto itself? And it does not. It creates something cool, but it doesn't map perfectly onto itself. So what I'm going to do when we're talking about symmetry of a figure, we're actually going to get rid of the graph, and we're just going to look at the figure on its own. And so there we go again, reflecting it, it doesn't map onto itself. And I want you to think about, where could I put that line so that when I flip the purple triangle over the line, it looks just like itself. And so hopefully you can see that if I connect one vertex with the midpoint on the opposite vertex, that slices this equilateral triangle perfectly in half. I don't know if I'm perfectly lined up, something like close enough. Okay, now if I reflect it, it maps perfectly onto itself. And you can see that because my line probably isn't quite where it should be, you can see a little yellow over here. But if I move it much more, then you can really see that is not the line of symmetry. So to get, this is called the line of symmetry, you want it perfectly lined up, like that. And I want you to think right now, how many lines of symmetry are there on this triangle? This is one of them. Are there more? And so I'm hoping you can see there are. I'm going to draw them in. If we connect this vertex to the midpoint of the opposite side, that creates another line of symmetry. That kind of cuts our equilateral triangle perfectly in half. And there's one more, and that's there. So this triangle has 3 lines of symmetry, and this is an equilateral triangle. We're going to try the same process, this time with a parallelogram. So I've got this guy here, this parallelogram, and you can see that right now it is reflecting across that red line. That's my line of reflection. It's kind of fun. You can make cool designs. But anyway, there's my parallelogram, and I'd like to see if I can move my line of reflection on the purple parallelogram so that the reflection perfectly matches it. and we say maps onto it and maps onto itself. So let me get rid of the reflection. The first thing you might try is, let me see if I can adjust this a little so we can see it better. Okay, there we go. So there's my reflection. The first thing you might try is sort of going from vertex to vertex. So maybe we'll try going from this vertex to this vertex. And then I just want you to think, when I reflect it, will that map onto itself? And surprisingly, it doesn't. So what if we go from this vertex to this vertex? Let's try it. Not even close. It's cool, but that's not a line of symmetry. What if we try going like from midpoint to midpoint? Like that. Do you think that'll work? Nope. What if we go from this midpoint to this midpoint, like so? Nope. Doesn't work. I don't really know what else I would try at this point. I mean, you could try doing something weird, but there is actually no way to cut this parallelogram in half. So this parallelogram has 0 lines of symmetry. It does not have line symmetry. You might wonder, what if we do a rectangle instead? So I don't know if that's a perfect rectangle, but a rectangle definitely does have line symmetry. So we can cut this rectangle a few different ways. You might want to start midpoint to midpoint, and I hope you can see that will cut it in half. We could go from this midpoint down to this midpoint. That'll cut it in half too. What about trying to go along the diagonals? Do you guys think that will cut it in half? It doesn't. So this rectangle, I'll draw in the lines of reflection for you. There are 2 of them. There's that one, and there's that one. So this rectangle has 2 lines of reflection, or 2, I guess we could call them line symmetries. Let me get rid of those. And I want to attempt here to turn this into a square instead of a rectangle. I don't know if I'm going to be able to. Let's see. Okay, getting there. All right, that looks square-ish, maybe. Oh man. Well, it doesn't look perfect. But a square has more, because on a square, obviously we can go up and down, and we can go left and right and cut it in half. But if it's a perfect square, which I don't think mine is, if it was a perfect square, then we would be able to cut it in half diagonally as well. And you can see mine isn't perfect, but if it was, you'd be able to go diagonally. So a square, we're pretending this is actually a square, has 1, 2, 3, 4 lines of symmetry, like that. So there's one more I want to show you, and this is a regular hexagon, so all 6 sides are the same, and right now I have the line of reflection over here, and it will create that yellow figure. And if I want to look for line symmetries on this hexagon, I can see there are a bunch. So you might first try going from vertex to vertex, and you should be able to see that that is going to create a mapping of itself. And we have many ways of doing that, right? Because I can also go from this vertex to this vertex, and from this vertex to this vertex. So those are 3 lines of symmetry on the hexagon right there. 1, 2, 3. We can't count these over here because they're part of the same line, right? So we have 1 line, 2 lines, and 3 lines of symmetry. But there are other things I can do. So, whoops, I didn't want to do that. Let me draw this last one in black. Now I'm going to move my red line of symmetry here, because with a hexagon, we can also go from midpoint to midpoint, and I'll show you that that does make a perfect mapping. So that's another one, and then we could go from those midpoints and from those midpoints. So this hexagon actually has 6 different lines of symmetry. So back to our notes, we're going to try to get this down. So there are 2 types of symmetry. The first is what we just talked about, and that's line symmetry. So go ahead and write line symmetry. Whoops, missed my R. Line symmetry. So line symmetry is when a figure maps onto itself when reflected over or across. Those 2 words are kind of used interchangeably. Over or across a line on the figure. And we'll go ahead and draw out 2 of the examples that we looked at. One was an equilateral triangle. So we'll just do our best to draw an equilateral triangle. And we saw that there were 3 lines of reflection. There's the one that goes there through the midpoint. And basically you can connect each vertex to the opposite midpoint, and that will create a line of reflection. So if we fold the triangle over any of those lines, it will map perfectly onto itself. So that has 3 lines of symmetry. We also looked at a hexagon, and it's a little bit challenging to draw a perfect hexagon, so we're just going to do our best, sort of like this. And this is a regular hexagon, which means in theory all the sides and all the angles are the same. Mine is not perfect, but we're going to pretend. And I don't know if you remember, but this one actually had 6 lines of symmetry. And I don't think I have 6 colors, but let's see what I can do. We can connect 1, 2, and 3 like that, and that's going from midpoint to midpoint, but then we can also go vertex to vertex. So that's 4, 5, I do have 6 colors, 6. So that guy has 6 lines of symmetry. All right. And then we also looked at a parallelogram. So let's just draw that. A parallelogram like this. And that actually had 0 lines of symmetry. So next we're going to talk about rotational symmetry. We're going to spend a lot of time in class exploring rotational symmetry, so we're going to keep this really quick today. Rotational symmetry is very similar to line symmetry. With line symmetry, you're looking for a line that you can reflect the shape on to map it onto itself. And for rotational symmetry, it's the same but with a rotation. So a figure maps onto itself when rotated around a point on the figure. So that's actually all the notes we're going to take. We are going to put a lot more on this page, and in fact I don't even need you to do a summary today because we're actually going to finish these notes up in class. So I just want you to get this definition down, and then we'll kind of complete this page in class. But before we do that, I do want to just very quickly show you a quick demonstration. Let's see if I can pull this up. So we have this triangle, and I just want to remind you what a rotation looks like. So mostly we've been rotating around the origin. So if I take this equilateral triangle and I rotate it around the origin. I'm changing my angle of rotation. There we go, right? That's a rotation. And I can move this point. So I could move it closer and try rotating around that point, and you can see what that does. I could even put this point on the triangle somewhere and rotate, which is kind of cool. But none of that has anything to do with rotational symmetry. Rotational symmetry would be when I can rotate it and have the triangle map perfectly on top of itself. And in this case, the only time that happens is if I go around 360 degrees. And that's kind of pointless, right? Because if we rotate anything 360 degrees, it'll fall back on itself. So I'm looking for where else I can put this triangle, this point of rotation on the triangle so that I'm looking for the center there. So that when I turn it, nope, I didn't get it quite right. But ideally, there we go. Now, I think I have it in the center. So when I rotate it, boom. So I've only gone 120 degrees around, but that yellow triangle now falls perfectly on the purple triangle. And that means that this equilateral triangle has rotational symmetry. And it'll happen again right around 240 degrees. And then if I go 360, I'm back on itself. But this triangle has rotational symmetry because bam and bam. And I can show that to you again with this guy. I know you can't see the whole thing, but I have a big protractor here. And you can see that if I turn this triangle, it falls on itself at 120 degrees, and it falls on itself again right there at 240 degrees, and that means this has rotational symmetry. Oh, I wish you could see this whole thing. Let's see if I can zoom out. Nope. Let's see. Zoom out. There we go. All right, so here I'm going to rotate my, my square. So you can see that as I turn it, bam, it lines up right at 90 degrees. And then it will line up again at 180 degrees, 270, and 360. So that means that this square also has rotational symmetry. So we'll finish this lesson up in class. For now, don't worry about a summary, you're done.